Okay, we quickly calculate the determinants of these four matrices, and this is very simple. We have 1 times 1, which is 1, minus 0 times 3, which is 0, which gives us 1. We have 1 times 1, which is 1, and k times 0, which is 0, so it's 1 minus 0. Again, it's 1. This matrix, main diagonal gives us 0, secondary diagonal gives us 1, so we get 0 minus 1 equals negative 1. This matrix, 1 times 5 gives us 5, 0 times 0 gives us 0, we get 5. Okay, well, let's think about this. What is this matrix? This is an elementary matrix. Okay, so these are elementary matrices. Very simple 2 by 2 elementary matrices, because we don't yet know, we will very soon, right here. We'll know how to get a determinant of a larger matrix. But for elementary matrices, well, what does this elementary matrix do? We should be well versed by today on elementary matrices. And we can see that this matrix was obtained from the identity by adding 3 times the first row to the second. Okay? So this is a matrix that added a multiple of 1 row to another. Now this is a very specific multiple. It added 3 times the first row to the second. What did this do? Well, this matrix, and you should pause and think about what this matrix does if you don't understand. This matrix adds k times the second row to the first. Now k could be any number. So this represents a matrix, any matrix, that adds a multiple of the second row to the first, and we see that no matter what k is, the determinant is still 1, because k is still multiplied by 0, whatever k is. So whatever multiple of the second row we add to the first, the elementary matrix will have the number of the multiple here, which in calculating the determinant will be multiplied by 0. So again, we just end up with the main diagonal, which is always 1 when you're adding a multiple of a row to another. Okay? Now what does this elementary matrix do? Well, you should again stop and immediately and ask yourself what it is. But you should immediately identify it as the matrix you get when you switch the rows of the identity. So here it is, and this matrix multiplied by another matrix will have the effect of switching the first and second rows. And the determinant of this row switching matrix is negative 1, because of course switching puts the 1s on the secondary diagonal and 0s on the primary diagonal, so we get negative 1. So when a matrix switches 2 rows, determinant's negative 1. If we add a multiple of 1 row to another, we get 1. Now we proved it. If we add k times the second row to the first, you should think, how would you prove it if you add any number k times the first row to the second? Does that give you an elementary matrix whose determinant is 1? You'll find that it does, and I think you can do that rather easily. You should stop and do that if you haven't. Now this matrix, we've multiplied the second row by 5. And what do we get? We get a determinant of 5. So if we multiply a row by a number, it should be pretty clear that whatever that number is going to be in one of the diagonals, whichever diagonal, the diagonal in whichever row we multiplied, and the other number in the main diagonal is going to be 1. So that if we multiply a row by a number, that's the determinant. Okay, so we have these rules. And those are the only kind of elementary matrices there are. Adding a multiple of 1 row to another, determinant is 1. Switching 2 rows, the determinant is negative 1. Multiplying a row by a number, the determinant is that number. Okay, now we saw previously that we row reduced a matrix, kept track of the elementary matrices, and we established that the matrix was then the product E1 inverse, E2 inverse, E3 inverse, E4 inverse. And if you don't understand that, well, we've just gotten the homework for the sections on elementary matrices, so you really should understand that unless you somehow missed the homework. And if you did, you really need to do that homework soon so you understand what we're talking about. Okay. Anyhow, then we developed this in class in detail. Review the videos related to elementary matrices from a little over a week ago. So we know that we can, if a matrix can be reduced to the identity, that it can be expressed as a product of elementary matrices. And these elementary matrices are the inverses of the matrices we would use to reduce our matrix. And, you know, the first one that gets, well, no, they're in the reverse order in which they were used in the reduction. In other words, E1 was used first in reduction. E1 inverse will be the first matrix on the left here, and then so forth. Okay, well, we haven't established it, but it's fairly easy to establish the theorem that says that when you multiply an elementary matrix by another matrix, the determinant of the product you get is the product of the determinants of the two matrices. So you multiply the determinant of the elementary matrix by the determinant of your other matrix. So the determinant of A would end up being just the product of the determinants of your elementary matrices. And remember, the determinants of your elementary matrices are 1 or -1 or possibly a multiple or the reciprocal of that multiple. Reciprocal of the multiple, if you multiplied by 5, a row by 5, then the inverse would be multiplied by 1/5, right? So take that. Again, I don't want to talk about that. We talked about that extensively already. Okay. If you need to see that, go back and look at it again. So determinant A is the product of these determinants, and if we keep track of the elementary operations, we'll know what the determinants of those elementary matrices are. So we can just multiply them and we get the determinant of A. Now for a 2x2 matrix, it's very easy to just calculate the determinant, you know, this diagonal minus this diagonal. But for a very large matrix, as you're going to see, the calculation of the determinant can get pretty arduous. Matter of fact, can get impossibly arduous, even for a supercomputer. Okay, unless you use some of these shortcuts. So I'm saying that in general, using elementary matrices, it's easy enough to prove that the determinant of AB equals the determinant of A times the determinant of B. Now that's something we'll talk about in a little more detail, but it comes down to the fact that A reduces to elementary matrices, either that or its determinant is 0. B either reduces to elementary matrices or its determinant is 0, and so forth. So I don't want to say any more about that, just say that the connection here with elementary matrices is what we use to prove this result. Okay, now we want to talk now about how to calculate the determinant of a matrix that's bigger than 2x2.